All right, let's see a little bit more about virtual memory. First, very briefly about how virtual memory is used as a tool for memory protection, which I talked about in the previous video, and then a little bit about how memory mapping works at the operating system level, and particularly at the level of a program that wants to map something from disk into virtual memory. So in the page table, what I showed you before was not entirely accurate. So if you remember previously, I showed a page table as consisting of a bunch of entries, each of which had a valid bit and then had an address either of something in physical memory if it was valid, or something on disk if it wasn't valid, or possibly null if it's not valid, indicating that it's not mapped at all. But actually, the page table entries have additional information associated with them. On our processors, that's a set of 4 bits. So I'll come back to soup in a minute. Read indicates that the process is allowed to read the page. In particular, if that is not set, then we have some memory that's mapped into our program that we can't access. Usually, everything that a process has mapped will be mapped as readable, but there might be a few exceptions. Next is write. So the write bit, as you might expect, controls whether the process is allowed to write into that region of virtual memory, into that page. If the write bit is no or false, then when the process does attempt to write to that page, we'll have a page fault, and the operating system can handle that most likely by terminating the process, a segmentation fault. There's also on more modern processors, all 64-bit x86 64 processors, and some x86 processors before that, some of the later ones, have something called an exec bit. So this controls whether we're allowed to execute things that are in that memory. You might remember that one of the mitigations that we had against buffer overflow attacks was to mark the stack as non-executable. And if we do that, that ensures that I can't just take code that I've stored on the stack somewhere in a buffer that I'm overflowing and set the return address to that code and run it. If I try to, the processor will notice that we're attempting to run something in a non-executable segment and will, again, crash the program. And then finally, there is the actual address. This soup flag is short for supervisor. So this means that the process, if this bit is set to true, the process itself is not allowed to access that memory. But the operating system running on behalf of that process is. So if the operating system's running, the CPU will have higher privilege and will be able to access things with the supervisor bit. And if it's running just as the program, then it will not have access to those pages. So we can use that to make sure that the kernel, the part of the operating system that's usually resident in memory all the time and handles the very core of what the operating system does, it can be loaded into memory, so it doesn't have to be paged out all the time. We don't have to change those page table entries, but processes are still not able to access that directly. They can't go around the operating system by writing to or even reading from its memory. And in a different process, we might have a different set of pages mapped with different permissions, and those will apply. One thing that modern processors have, or they can be configured to do, is something called W XOR X, which is short for write, exclusive, or execute, meaning that a page can either be writable or executable, but not both. So if we enable that, that avoids a lot of the problems that we have with buffer overflow attacks. Even if we were able to overflow a buffer in the heap, something that is writable, the hardware and the operating system together can ensure that that's not executable. Okay, so moving on, I wanted to talk a little bit about memory mapping from the point of view of the operating system, and even more importantly, from the point of view of someone writing a program to run on an operating system like Linux. So, virtual memory areas, things that we have in virtual memory, like the text section of our program or the data section of our program, are initialized by associating them with particular areas of disk. This is called memory mapping. So when that happens, the area of virtual memory can be, we call it backed by, that is, it is caching or it is standing in for a particular location in either the disk, so that could be a regular file, that might be the executable file when the loader, execve, loads it into memory. That could be a file that we are trying to read from or write to in our program. Or it can be backed by an anonymous file, which really means there's not actually a file there. So if I do that, then the first time I try accessing that page, there's not really a disk address associated with it. So the hardware and operating system will give me a page full of zeros, a demand zero page, when I first access that. And then once the page has been written to, well, if it's going to be evicted from memory at some point, it does need to be associated with some region on disk, and that would be something like swap space. So once a page is written to, it does refer to an area on disk, even though that might not actually correspond to a file. So we have this swap file, or sometimes a swap partition, more often these days a swap partition, part of the disk or a file on our file system that is dedicated to holding things that need to be moved out of main memory but aren't backed by a regular file, so we can't just write to that file. Instead, we'll write to the swap file, we'll point that page in virtual memory to that page in the swap file or in the swap partition. So this allows us to do something a little more complicated when we have things that are shared between multiple processes. So, for example, I might have two copies of the same program running. Now, those programs are going to have two things, more than two things, but two things at the moment stored in the executable file that get mapped into virtual memory. It's going to have its code along with, usually in an adjacent region, read-only memory. So those things, we'll say, are up here, but it might also be data. Now, if I have two copies of the same program running, then they are going to need different data in physical memory eventually. Once I write to that memory in one of the processes, that shouldn't be reflected in the other processes. Even if two processes start out with the same values for their global arrays, for example, as a process changes things, we don't want that to step on the toes of other processes that are run from the same executable file. And remember, Linux operating systems can have several users at a time, so even if I couldn't expect the same person to be running two copies of a web browser at the same time, for example, I might have two different users, one of whom is running the web browser and the other whom is running the web browser. So how do we handle the things like the data segment of that process? We want them to be mapped into virtual memory somewhere, but when I actually write out to that, I need something special to happen, which is I need to do copy on write. So when those processes start, again, two processes running the same executable file, so loading the same data, but they don't want to step on each other's toes by writing to each other's data, those are mapped to a section of physical memory, and they are mapped to the same section of physical memory. So when one program loads in its array, when that program starts up, the next process referring to the same program doesn't have to load it from disk again, it's already there. But if one of these processes now needs to write to that page, I have a problem because the other process should still be referring to the original version of that page. So something like that in the page table is marked as read only. So then a process tries to read from it. It gets a page fault, and the operating system knows that this is marked as copy on write. Even though it's read only as far as the memory management hardware is concerned, it's actually copy on write. So the operating system, rather than doing the usual thing about just changing the value, I'm writing to a non-writable page, so instead of terminating the program, instead the operating system makes a copy of that physical page and updates that process's page table to point to that copy. So now if process 1 refers to something at that address, it's still referring to the original, but if process 2 does, it's referring to its changed copy. Now we have to mark it as copy on write in both processes so that if process 1 tries to write to that memory area, it's going to get its own writable copy of that page. And the important thing here is that we're deferring that copying as long as possible. Only when there actually is a difference between these two pages, when one of the processes has written to them, only then do we actually go and make a copy. All right, so on to the last topic of the lecture and the last topic about virtual memory, memory mapping from the programmer's point of view. So it turns out there's this system call called mmap. Rather than show you the slides associated with that, let me switch over to the virtual machine. All right, so I'm in the Lecture 11 directory, but actually I wanted to first look at a manual page, the man page for mmap. So I type man mmap, I get this in my window. I wanted to point out a couple of things. If you remember, if you looked up the man pages for malloc or for Sterlin, for example, those said malloc or Sterlin parentheses 3. mmap says parentheses 2. This number is the section of the manual that this command is described in. Section 3 is for library functions, and you might imagine mmap is a standard library function, and it kind of is, but really it's something called a system call. Mmap, mapping memory, changing those page tables, is something a process isn't allowed to do for itself. Rather, the kernel, the operating system, handles that for it. And the process, in order to get the kernel to do this, makes a system call, which we'll hear about in a later lecture. So anyway, mmap is a system call. There's also a wrapper in the standard library that knows how to call the system call, what arguments it takes, and so on. Mmap will map, or for the related unmap command, unmap things from disk to memory, files or devices. We won't worry much about devices right now. So it takes several arguments. It takes an address. So this is a void star. Remember in C and C++, void star means a pointer to nothing in particular. I'm not specifying what kind of thing is actually stored in that memory. To use it, I would need to cast that void star into a char star or an int star or so on. So this is the address. This is from the program's point of view. So this is a virtual address that I want to map something to. Now this had better be a virtual address that isn't currently mapped. And there are ways that I can find something like that for my program. A region of virtual memory that I'm not using yet. Then I specify a length. I need to know how much stuff from disk do I want to map to that region of virtual memory. If this is a file, for example, I need to specify either the size of the file or maybe the size of some subsection of the file. For example, if I'm loading an executable file, the execve function, and I wanted to do a memory mapping for the text segment, I would need to specify the length of the text segment, which I can get from the elf header. I can also specify protection flags. So these indicate whether the memory should be readable, writable, executable, and so on. Other flags. So these are other things that might apply to it. Is this anonymous or file backed? Is it shared, or is it private to this particular process? A file descriptor. We'll see more about file descriptors when we get to the file system and system calls in a later lecture. But this is something that refers to a particular file that the process has opened. And an offset. Well, remember, we can specify the length to be less than the entire length of the file. The offset allows us to start not from the beginning of the file, but a little bit later. munmap releases a memory mapping. It only needs the address and the length, and with that together, it can remove the memory mapping. So if you read the description in the man page, and I'm not going to go through it in detail, you can see the kinds of things that you need to specify in each location. In particular, the address can be null. If that's the case, then it's up to the kernel to choose the address. Now, in most cases, I don't necessarily know as a programmer which addresses in my program are going to be used and which are not going to be used. And even if I could know that, I could keep track of it, I'd rather not. So if I don't have any strong preferences, then I can specify an address of null and make sure that the kernel chooses the address for me. Also notice that if I did specify an address, it's only treated as a hint. The kernel doesn't guarantee it'll load the thing at that particular address. In fact, it has to load it at a page boundary. Remember, pages are something like 4 kilobytes, so I need to load it at a multiple of 4 kilobytes. So on Linux, it will try to choose something nearby. So then how do we find out what address it was mapped to? Well, that's what mmap returns. It returns the address that the file or the anonymous file was actually mapped to. And so we shouldn't just rely on the address we pass in. We should always look at the return value. As far as those protection flags, I can specify protection none. So these are constants. Or I can specify these things, exec, read, or write. And I can use bitwise OR, so the vertical bar operator, to join these together. So where do I get these? Where do I get the definitions for prot exec, prot read, prot write? Well, scrolling up in the man page again, I can see that's in sys/mman.h, short for memory management. And then the flags, there are a lot of different flags. I'm not going to get into them, but the important one here is it can either be a shared mapping, so if other processes map the same file and write to that address in memory, then they're going to be seeing the changes that each other made. And also writes to that will be reflected in the file on disk. So map shared might be used, for example, if I'm opening a file and I want to update it, and I also want another process to be able to do the same, so they can pass information back and forth that way. Private mappings are copy on write, as we talked about before. So if I write to something in that region of memory, then that doesn't get written out to the file on disk. Instead, if it needs to be evicted from memory, it'll go to the swap file. And also, other processes that map the same file will have their own copy on write version. So this would be used, for example, for loading the data section of a program into memory. For one thing, as I talked about before, if I'm running multiple instances of the same program, I don't want them to overwrite each other's variables, so that needs to be private. Also, if a program writes to one of those global variables, that shouldn't change the executable file. That shouldn't change what happens the next time I run the program. I want everything to go back to the way it was. And then there are a bunch of other flags. Map anonymous is used for doing an anonymous map that isn't backed by any file, that instead goes to the swap file or the swap partition. So this can be used to just request the operating system to give us a certain amount of memory. This is one of the things that malloc can do to get its memory from the operating system. Now, the operating system will only give us whole pages at a time, so malloc will use mmap and maybe some other tools to map a large region of memory, and then keep track of its own data structures to parcel those out to different calls to malloc, so that if you request a 10-byte region, malloc might actually request a whole page, give you 10 bytes of it, and then it has the remaining 4,086 bytes for subsequent calls to malloc. So the other flags I'm not going to go through. I did want to show you one small program, although we're not going to be able to talk about all the details of it because some of them are going to involve things we'll get into in a later class. But this is in the Lecture 11 code. It's called mmapcopy.c. So this is a program that copies a file by using mmap and the write system call. We'll talk about the write system call later, but for right now, just know that it takes a file descriptor. One refers to standard output, so this is going to write the contents of the file, copy them to standard output. It takes a pointer to a buffer, which is up here. I'm going to get that from mmap, and it takes a size, and it will write the contents of that buffer to the specified file. In this case, it'll actually write it to the screen. We're using the mmap system call here. Actually, we're using a wrapper around mmap and write. So these wrappers, beginning with a capital M, belong to this file, csapp.c. This is a collection of wrappers provided by the authors of the textbook. The header file associated with that is csapp.h. These give us a little bit error-prone or a little bit less error-prone ways of doing various kinds of system calls or library functions and so on. In particular, this mmap call, if it gets an error, which would be represented by mmap returning null, will automatically terminate the program rather than just giving us a null pointer to then crash a little bit later. And it will, in that process, also give us a message. So you can look at the code for these, capital M map, capital W write, in the csapp.c. So our call to mmap, we're giving null as the address, meaning we don't care what address the kernel gives us as long as it's something not already in use. The size comes from the size parameter to this mmap copy function. So this will be the size of the file. We're asking for it to be readable. We want to have a read-only mapping of the file, and then we're going to write that out to the screen. We want it to be a private map, so if someone else changes the file, I won't see those changes. This is the file descriptor that we're going to read from, and we'll see in a minute how that's opened down in main. And 0 here is the offset, meaning we want to start from the beginning of the file. So once we've mapped it, we'll write it out. So notice here that we've taken what would usually be a two-step process. Read from the file into a buffer in my code that I've initialized maybe on the stack, or maybe that I've gotten from malloc. So that is, well, I have to load things from the disk into memory. The operating system does that for me through the virtual memory system, and then I'm copying from that memory into different memory. But here, I'm referring to that memory that the operating system is mapped for as directly. So that saves us one copy when writing this out to the screen, or it could be to another file if we changed the function a little bit. So down in main, the program takes a command line argument. If that's not specified, it will exit. It opens that file. This is another function from the CSAPP library that's a wrapper around the open system call that we'll see in a later class. It opens it read-only. If I had opened it read-only and asked for a writable mapping, that might have been a problem. Since I have a private mapping, maybe not that bad. I use something called fstat to get information about that file. Again, we'll see more about that when we talk about the file system. But in particular, I want the size of the file from that information, so I can pass it to the mmap copy function. And then I just call mmap with the descriptor of the open file and the size. And then the program exits. So if I build everything here, and then I run the mmap copy program, and I ask it to read its own source code, mmapcopy.c, it will do just that, read it and display it to the screen, just like the cat command. Now, unlike the cat command, this is a very simple program. It doesn't handle multiple files or so on, but you can see how memory mapping can be useful if I want to deal with files. All right, well, that's all. So thank you very much for listening, and come back soon where we'll talk about something else. Thanks a lot.